Here we have a basic horizontal projection. We have a ball that's being rolled horizontally over a table of some sort, and it arcs its way down to the ground. We are given the velocity Vx, that's how fast it's moving in the x direction originally. It's not moving up and down at all, so there's no Vy component. And we're given the height of the table. We want to find the range, which is the variable delta x. There are two steps to this kind of problem. One is to find the time in the air. Now, the only thing that affects the time in the air is how high it falls from. The horizontal velocity does not affect it at all. It's going to fall down this 3 meters the exact same time, whether it is moving at 2 meters per second horizontally or if it's just simply dropped straight down. So the height is the thing that affects it here. The higher the fall, the longer it's going to be in the air. So the equation that we use in step 1 is the exact same equation that we used when we found the time for something to just simply drop straight down. For the h, we put in the 3 meters, 9.8 at the bottom. If you do your math here correctly, you should get a time of 0.78 seconds. That's the first step. The second step is to find the range. While this ball is in the air, it is moving horizontally 2 meters for every second that passes by. And we're in the air for only 0.78 seconds. So we're not in the air for a full second at all. So we're not going to go 2 meters, but exactly how far will we go? We use this short equation. Delta x is the range, Vx is what we're given, and the time we just figured out. So the Vx once again is 2. The time is 0.78 from the previous step. Multiply those together and you get 1.56 meters. Second problem. We have a stunt driver who wants to drive a car off of a cliff and land on a boat. The cliff is rather high. It's 9 meters, about 27 feet. And the boat is stationed 12 meters away from the base of the cliff. We want to know how fast the car has to drive. The two steps are going to be using the same two equations as before. The first step, we need to know how much time the car is in the air. The longer it's in the air, the slower it can go and still make it in the boat. So the equation is the same one as before. We're finding the t. The h here is going to be the 9 meters from the cliff. So we have 2 times 9 over 9.8. When you take the square root of all of that, you get 1.35 seconds. The second step then is to find the velocity of the car, and we use the same equation as before. It's just that in this case, we're going to be finding the Vx, how fast it's moving horizontally. So the delta x is the 12 meters that it has to span between the boat and the cliff. And the t is the time in the air that we just figured out a moment ago. So to solve for v here, you have to divide both sides by 1.35. 12 divided by 1.35 is going to be 8.89. And that's a velocity, so the units are meters per second. The other kind of horizontal projectile that we had was when it went from one building to another. It is still thrown horizontally, but it arcs its way down to another height that is above the ground. We're given the original height, we're given the final height, and we're given the gap in between. These kind of problems are asking for the velocity that you have to throw the ball in order to make the gap. The first step is to find the flight time. And the bigger the difference in the two buildings, the longer it's going to be in the air. So when we do the flight time or the flight time equation, the h here is the difference in the two buildings. This building is 19 meters. This building is 12 meters. So it's going to fall a distance of 7 meters, and that's what we put in for the h. Do the math here, and you'll get 1.2 seconds. During that 1.2 seconds, it has to span 20 meters. So, to find the velocity, we put in 20 for the delta x, the v stays a variable, and the t is the 1.2 seconds from our previous step. Divide both sides by 1.2, and you get 16.7 meters per second. Those are the three kinds of horizontal projectiles. Now we have an angled projectile. We have a motorcycle that's going to be going up a 40-degree amp, and the velocity is going to be 20 meters per second, about 45 miles an hour. We want to know how far will the motorcycle go. The first step is different than the first step of the horizontal projectiles. We have to know the Vx and the Vy components. We have to know how fast the shadow is moving across the ground, and we need to know how fast it's rising in altitude as it goes up the ramp. The Vx, the speed of the shadow, is found always by multiplying the launch velocity by the cosine of the angle. So 20 meters per second times the cosine of the 40 degrees gets us 15.3 meters per second. Make sure that your calculator is in the degree mode, and different calculators will make you type in these numbers and the cosine button in different orders. So you gotta make sure you have the right order. This is how fast the shadow moves across the ground. Now, how fast it's rising as it goes up the ramp. We use the sine of the angle multiplied by the launch velocity. So 20 meters per second times the sine of 40 degrees gets us 12.9 meters per second. The second step then is like doing the horizontal projectiles in terms of the goal, finding the time that's in the air, but it uses a different equation. The other equation we used was only for things going downwards. This object is going both up and down, and so it's a little bit more tricky to figure out. One way of doing it is with this Vf equals Vi plus At equation. We're looking at only the vertical components of the velocity, because the faster it rises in altitude, the higher it's going to get and the longer it's going to be in the air. The horizontal velocity doesn't really affect the time in the air at all. So the final velocity is going down, negative 12.9. The initial y component is going up, positive 12.9. Those were coming from this Vy here. The acceleration is caused by the force of gravity. It's always downwards, negative, and we have the 9.8 for the size, times the flight time that we're trying to figure out. To do this, you first subtract off 12.9 from both sides, and then you divide by negative 9.8, and you'll get 2.6 seconds for in the air. The third step is to find the range exactly like we did before with the horizontal projectiles. Same equations being used. We're looking for the delta x, and so that stays a letter. The Vx we found earlier way up here with the cosine, and the time we just figured out in the previous step. So multiply 15.3 times 2.6 and you get 39.8. Now remember, there's another way of doing the flight time. We have this shortened version. This t equals Vy over 4.9 is the same thing as this, just rearranged. So the Vy is the 12.9 from our sine function. 12.9 divided by 4.9 is 2.6 seconds. The same thing as what we got before. One more example like that. We have a rocket that's being launched at 50 meters per second, about 100 miles per hour, and the angle is 70 degrees. We want to know the range. The first step is to find the components, Vx and Vy. Vx is V cosine of theta. When we put in the numbers, the V is the 50, the theta is the 70 degrees. Type that in and you get 17.1 meters per second. To find the y component, we multiply the launch velocity times the sine of theta. So that's going to be 50 times the sine of 70, which equals 47 meters per second. That's the first step. The second step is to find the flight time. Using the Vf equals Vi plus At equation, again using only the y components at this time. The final y component is going down, negative 47. The initial y component is positive, going up 47, minus 9.8 for the acceleration, and time is what we're looking for. Solve that correctly, you'll get 9.6. You do that first by subtracting 47 from both sides, and then dividing by negative 9.8. You could also get the same thing by just dividing the y component by 4.9. So you get 47 divided by 4.9 is again 9.6. The third step is to find the range. Same equation as always. You're looking for the delta x. So the Vx we figured out before with the cosine function. It's a 17.1. The time we figured out in the previous step, 9.6. Multiply those together and you get 164.